Hello, so this is on Wireguard, which is fast, modern, secure VPN tunnel. So some background, I'm Jason Donenfeld, run a security company, and my background is primarily in exploitation and finding kernel vulnerabilities, crypto vulnerabilities, mostly in breaking things. But I've also been doing kernel-related development for a long time, and I wanted to make a VPN that would avoid a lot of the things that a lot of the problems that I've seen when doing offensive research. So what is Wireguard? It's a layer 3 secure network tunnel for IPv4 and IPv6. And as we'll see throughout this presentation, it's very opinionated. So in this case, it's only layer 3. It only works at the IP level. It doesn't do layer 2 Ethernet frames because I don't think that's the right way to design your network. I don't think that's a good way to do tunneling. And so it only does layer 3 because it's a very opinionated design. It's been designed specifically for the Linux kernel and the Linux kernel networking idioms, but we do have cross-platform implementation available, and hopefully we'll be porting to other kernels as well. It's UDP-based. It doesn't use its own IP protocol, which means it gets through most firewalls in the normal way that UDP gets through firewalls. We've tried to use modern cryptography, but also fairly conservative cryptography, nothing too newfangled. And the emphasis of the project is on general simplicity and being really auditable. We want people to be able to sit down, read the code, understand the project, and make sure that it's doing what we say it does. The authentication model is extremely simple. It's just like SSH's authenticated keys, where both sides know each other's public keys ahead of time, and then they can talk to each other. There was a presentation in here before about OpenVPN and some problems with it. So Wireguard is a replacement for OpenVPN and the other big standard of IPsec. Now, the code base for this actually grew out of a stealth rootkit project I was working on, where I needed to stay embedded in a network for quite some time without being discovered and get data in and out securely. But it turns out that a lot of these things that you do for stealth in an offensive setting turn out to be really useful in a defensive setting when you just want to have a legitimate network tunnel for yourself. So this first idea of being easily auditable, when we look at the code counts for these other projects, OpenVPN, 116,000 lines of code, plus you need all of OpenSSL in order to run it. The Linux XFRM layer, which is like kind of the symmetric part of IPsec, is 119,000 lines of code. But then you need Strong Swan for the key exchange, and Strong Swan is massive, 400,000 lines of code. Soft Ether is kind of this jack of all trades user space program that implements a variety of VPN protocols. This is 300,000 lines of code. I mean, this is a lot of stuff that is going to be very difficult, has been very difficult for people to audit because it's so big. Wireguard, in contrast, is less than 4,000 lines of code. So when we visualize this, kind of the solar system of VPNs, Wireguard is the Pluto over there. And this is really important. We want the project to be one that any security researcher on the weekend, just because he's curious, could casually open it up and check things. When you have a massive code base, maybe you look at it as a security researcher because you've been paid to as part of a job or because you want to make a massive project out of it, but always it's a very cumbersome undertaking, not something you just casually waltz into. Whereas I think with Wireguard, with such a small code size, it resembles more of a toy in size. And so researchers will be more inclined just to take a quick peek because it's quick, it's small. The next thing we want is the simplicity of the interface. So if you've used IPsec before, maybe you've struggled with the Linux XFRM layer to make this happen, where you have transformation tables and policies. And it's very complicated. With Wireguard, instead you just get a normal network interface. So you can add the interface using IP link, you can give it IP addresses, routes, IP tables, Basically, all the things that you're used to doing with normal network interfaces, like ETA0 or WLAN0, you can do just the same with WG0, with WireGuard. As we'll see, even kind of antiquated things like etc host allow and deny become newly possible, newly secure with WireGuard. But WireGuard is also a little bit blasphemous. We've broken a lot of the really nice, pristine layering that 90s technologies like IPsec have. So IPsec, you get a transformation table that transforms packets by adding encryption or sometimes even compression. Yikes. And then this is managed separately by a user space daemon that does the keying, that updates a policy table and the transformation table. And it's all very nicely, cleanly layered, but that makes it super complex too. So with WireGuard, we just kind of get rid of all that. And our basic unit instead is the network interface. And then we build up from there. We try and use clever engineering tricks and clever organizational tricks to make it coherent again. So we start with something that at first couldn't possibly do what we need, encrypting things and accounting for different peers, but then we're able to gradually solve each of the problems that has, and we have something a lot simpler as a consequence. So how do we do this? We have this idea called cryptokey routing, where the fundamental idea is you have an association between a public key of a peer and the IP addresses that peer is allowed to be inside the tunnel. So let's look at the full list of things that WireGuard Interface has. WireGuard Interface has a private key. That's what would identify you. For example, it has a listening UDP port. So that's how to access your WireGuard interface on the internet. And then it has a list of peers. Each peer is identified by his public key. His public key is his name. And then it has this list of associated tunnel IPs, this allowed IPs. And these are the IP addresses that it can be inside the tunnel, not outside, but inside the tunnel. And then optionally, it has an endpoint IP and port on the internet that is, where do I send UDP packets to find that peer on the internet? So this is a really important concept. We bind the public key to the IP address, and there's always this one-to-one mapping between an IP address and public key. So if we look at just kind of an example text configuration, a server would have a private key and list on a well-known listen port, and it would say, all right, this peer can be in the /32 and the /24, the other peer can be in the /32 and the /16. But then on the client might want to say, all right, my allowed IPs is going to be 0000/0. So that would mean I trust the server to send me any packets through the tunnel, which would be the case if you wanted to use a WireGuard server for tunneling internet traffic, for example. So here's the flow of packets when you send things from user space. So you type ping, and this issues the send syscall. You send a packet. The Linux kernel then goes to the ordinary routing table, and it determines that this should be routed using the WG0 interface. Then WireGuard now has the packet, and we look at the destination IP address to determine which peer should we send it to. And then once we know which peer we should send it to, we encrypt it, and we send it to that peer's endpoint. On the other end, it works in reverse, where WireGuard will receive through its UDP socket an encrypted packet. It'll decrypt that, and while it decrypts it, then it will determine which peer encrypted it. Then it'll look at the source IP address of that decrypted packet and say, were I to be sending to this source IP address, would I send it to the same peer that just sent me this packet? So it's a kind of reverse path filtering there, but cryptographically enforced. And then once it checks out that indeed this peer is allowed to have sent that packet as that IP address, then it just hands it off to the rest of the Linux networking stack. So this model here makes system administration extremely simple. If it comes from WG0, and it comes from the IP address, say 192.168.517, and that's for Yoshi's public key, then we know it definitely came from Yoshi, and it couldn't have come from anyone else, cryptographically enforced. And so the IP tables rules for this kind of thing are plain and simple. It comes from the WireGuard interface, it's from the given IP address, and then you know it's authentically from who you want it to be from. So I mentioned this was simple. And the intent is that you set things up statelessly. So you have WG0 and it looks kind of like an ETH0. But of course, all network protocols that use cryptography, or most I should say, require some kind of state for things like forced secrecy or ongoing key exchanges and so forth. But WireGuard appears stateless to the administrator. So the way we do this is with a series of timers. And the timers manage all the session state invisibly behind the scenes. That doesn't require any configuration, and it just works. You turn it on and WireGuard starts working. We've tried to keep the timer model state machine extremely simple so that every transition between each state is accounted for. So we have no undefined corners of it. So we have 4 main events. User space sends a packet. Now, if there's been no session that's been established for the last 2 minutes, then we send a handshake initiation packet. If we don't get a response to that packet after 5 seconds, then we send a new one. Now, after we successfully authenticate an incoming packet, like a data packet we get from a peer, and we're certain that the peers actually sent it to us, then we wait 10 seconds. If during those 10 seconds we have a packet to reply, such as I send a ping, you send a pong, that's fine, we do nothing. But if we don't have anything to send within 10 seconds naturally, then we just send an authenticated empty packet. This way, if we've sent information, but we haven't received anything back within 15 seconds, we know something went wrong with the connection, and we send a new handshake initiation. Now, notably, this all stops when no one's sending anything. If no one's sending anything, I haven't received a message that I'm inclined to reply to, and so I don't reply, and so it goes silent, which is nice for stealth, as we'll see later. But while people are talking, we make sure that we'll continue to be able to talk successfuless with simple timer state machine. So as I mentioned, the interface is super simple. It's trying to be stateless to the administrator. We add an interface, you configure its peers, and then immediately you can just send packets. We try and have very few configuration knobs for this. And the goal is that if you set it up wrong, it just won't work, as opposed to setting it up wrong and then you have some terrible security catastrophe they didn't realize because it seemed to be working. No, but in this case, we want to fail safe. The endpoints also roam. So you don't actually have to specify where to reach a peer on the internet. If a packet from a peer arrives at your computer and it authenticates successfully, then if you want to talk back to that peer, you just talk back to wherever that peer was sending packets from. So this means if you put your laptop to sleep in one network and wake it up in another, it'll just keep working. It'll roam seamlessly to one from the other, from one to the other. If you have a mobile phone with Wi-Fi and cellular, and you switch between the two, it'll just roam automatically between the two of them. If you've ever used Mosh, which is kind of a UDP SSH, it's very similar in nature to that. So before we go further into how this all works, I just want to show a demo of what it's like to set it up so you have more intuition on what this all looks like. Okay, so we have a peer A and a peer B. So on peer A, we'll generate a new private key, WG gen key, and we'll do the same on peer B. And when we look at the private key, it's these very short base 64 encoded string. Then from the private key, we can derive a public key using WG pub key. Okay, now on peer A, we add a WireGuard interface. So add WG0, type WireGuard. We give it an IP address. This is just kind of normal, boring Linux networking stuff. And then we tell it, here's the private key that you should use, because we just generated this file in private. And then we set the interface up using IP link set up. Then we do the same on peer B. We have a WG0 interface, we give it an IP address, We assign it the private key that we've just generated, and we set it up. So now when we hit IP address, we can see the various interfaces we have. To start with, we have ETH0. That's like our internet-facing interface. So that's in the 192.168 range. And then we have WG0, and that's in like a 10/24 range. So that's inside the tunnel. So now let's tell the peers about each other. When we hit WG0, we see that they each have a public key and a private key now, and they're both listening on a port. And now we'll tell one to another with the amazing key exchange mechanism called copy and paste. Now, were you to be using this in a bigger setting, you could, of course, script this, use databases, even use TLS, it doesn't matter. But just for this, we're doing the initial key exchange through copy and paste, which I'm sure you've already done with, say, SSH. So we tell peer A about peer B, we give it the public key, and we say, here are the IP addresses that B is allowed to be in the tunnel, and here's its endpoint on the internet. And now we do the same thing. On peer B, we say, okay, here's peer A's public key. Again, copy and paste here. We give it the IP address that it's allowed to be inside the tunnel. And then we tell it, here's your internet-facing endpoint. And that's pretty much it with the setup. After this, we can just ping the other side, and it works. It's not more complicated than that. WireGuard does not do much more than that either. And when we hit WGNet, now we see they had a handshake and exchanged some data and all as well. But that's pretty much it as far as WireGuard. You have peers, and you can exchange keys, and then they can talk ever after. And you have this layer 3 interface that's continuously secure. It's intentionally small. WireGuard is intentionally the small building block that we want to keep secure, compact, easy to understand. And then from that, you can build more complicated systems. But we want the crucial element, the building block, to be as secure and simple as possible. So since this WG tool that we just used is very simple, you can build more complicated tools around it. So there's already integration around this tooling in the various network managers. It's in OpenWRT, it's in Gentoo's OpenRC, it's in Nixos, it's even in systemd now, in LinuxKit, it's in Ubiquity routers, it's in Network Manager. So it's a very simple interface, but then you can integrate it into other things. So here's one example is WG Quick is a little bash script I wrote that I now distribute with the tools because people seem to enjoy using it, but it's just a tiny dumb bash script that wraps IP in WG and adds a couple extra fields to a config file. It adds a post down, in case you want, and a post up and pre-up and so forth. In case you want to run some commands, you can set the address and DNS from within it. And then you just run WG Quick up and WG Quick down to have your interface instead of having to plug all the keys in manually. And that's great, it's convenient, works, run on my laptop. But at the end of the day, that's just a dumb shell script around these other smaller tools. And that's the kind of development that WireGuard encourages, where we have this nice building block, and then you can build up from that. It also works nicely with network namespaces, if you've used those in Linux before. The WireGuard interface can live in one network namespace, and a physical interface can live in another one. And you can choose where the socket that WireGuard is using to exchange encrypted UDP packets lives. So for example, you could let a Docker container only access the internet via WireGuard. You can only let your DHCP clients touch physical interfaces, but then let your web browser only see the WireGuard interface and nothing else. So for the container case, you might have in your init namespace your ETH0 and WLAN 0. And in your container namespace, like in your Docker place, you only have WG0. So when you look at, I have config output, within the container, the only interface those processes can see is WG0. The only way it has to access the outside world is through WireGuard. But meanwhile, the socket WireGuard uses is over in your init namespace. And so the encrypted packets go out through the interfaces you expect it to go out of. We can also reverse the whole thing. This is running on my laptop right now for the purposes of a security conference where I have in my init namespace only WG0, where in a physical namespace, or a namespace I call physical, I have my actual Ethernet adapter. So my DHCP client and WPA supplicant and all that can only see my physical interfaces, whereas the only way my web browser can access the internet is through WG0. And so we have a perfect separation, so I'm not going to leak any plain text by accident onto Black Hat Wi-Fi network. All right, so next principle in secure design, we want to have static fixed length headers. So all the packet headers have fixed width fields, so there's no parsing. And so we eliminate all parser vulns. This is kind of amazing. If we have no parsers, we have no parser vulnerabilities. Really simple, obvious, basic thing, but it's not done in practice. But when you do it, then you just get rid of years of security researchers coming after you, which is a lot different than what's been done with, say, ASN1 and X509, where you have these crazy formats, and every time it's been implemented, it has a bug. I don't know anyone that can make an ASN1 parser correct on the first try. So we don't give ourselves that challenge. Instead, we just have fixed width headers. We also have static allocations and guarded state everywhere. And this is a little bit harder to do in practice. So all the state required for WireGuard to work is allocated at configuration time instead of in response to packets. So we get a packet, we can't do any dynamic memory allocation, which is great, eliminates a lot of heap vulnerabilities, but it also places unusual set constraints on the cryptography we're using, because it means that we can only operate over a very finite set of state. Corollary of this is that no state then can be modified in response to unauthenticated packets, since then you could have an attacker use up all your finite state. So on one hand, it's great that an attacker can't use any state, eliminates another class of vulnerabilities, but also puts more constraints on the crypto. So interesting part of the WireGuard project is coming from this perspective of, okay, we want to code this in a certain way. We want to have these defense in depth techniques. All right, now how do we make the protocol so that we can code it in a way that's secure? Most network protocols are done in reverse, where you have a room of networking people and crypto people who dream up the best things they can, and then the poor implementers try and code it, and it's a disaster. So with WireGuard, we're trying to take into account both considerations at the same time. As I alluded to before, WireGuard is intentionally stealthy. Grew out of a rootkit project, so needed not to be discovered. And so it doesn't respond to any unauthenticated packets. You can't scan for it on the internet. And so it'll only respond to you if you send a packet that has the right cryptography in it. It's also nice because it's not chatty. So if you're using this on a mobile phone with limited battery, it's not going to be sending random useless junk all day, because it just goes silent when it's not in use. So to achieve this, we want to have solid crypto. We're using Trevor Perrin's noise protocol framework. The WireGuard project was involved really early on with noise, and so we went back and forth trying to make sure that noise would be able to fulfill the goals that we had for WireGuard, and what's come out is quite nice. Noise itself is kind of related in spirit to Signal protocol, similar set of ideas, though totally different protocol, because it comes from the same guy. And it has the usual list of desirable properties you'd want from a modern key exchange. We're also using modern primitives. We're using curve 25519. We're using Blake2 as a hash function. We're using cha-cha-20 poly 1305 as an AEAD. Now, importantly, there's no cipher agility. You don't get to choose. This is what we have, and if you've got a different opinion, sorry, this is what you get. If these are ever broken, then the policy will be to upgrade. Because why would you want to have broken networks, broken elements in your network besides secure elements? That's not the way to design a system. So if the crypto is broken, then you update your systems. And you don't leave around broken crypto for years, giving backdoors to attackers for a long time to come. This is quite a bit different from the extreme cipher agility with something like TLS, where you have a complicated negotiation that happens, which historically has been vulnerable to downgrade attacks and so forth. And it also means that we're not leaving around a bunch of antiquated crypto, which is good. So we have nice properties that come out of this protocol. We have strong key agreement, key compromise impersonation resistance. This is an interesting one. It means that if someone steals your public key, if your protocol is vulnerable to key compromise impersonation, it means that then I could impersonate anyone to you because I've stolen your public key. It's like if someone stole your wallet and then they could change your perception of other people's faces, and then you wouldn't, they could pretend to be anyone to you. So we're resistant to that. Unknown key share, so the two people are talking to each other and definitely their key hasn't been shared with one. There's key secrecy, there's forward secrecy. So we have a new session every 2 minutes. We're sure that sessions are unique. There's some limited form of identity hiding. And of course, there's replay attack prevention. But we still allow for the network to reorder packets, which is necessary at layer 3. IP networks do that. But we don't allow it to replay packets. And it might just be a bunch of crypto mumbo jumbo that you say, I don't understand that, and it looks fishy, and so I don't want to trust it. But in fact, we've formally verified this in a symbolic model using nice software called Tamron. So we have a proof that it's that it has these properties. Recently, there was another proof done in a computational model, and academics are working on this kind of thing. So we have some real assurance that the cryptography we've come up with, that the protocol we've come up with, is not bogus. So all these design principles before kind of combine into what we get from the key exchange. So first thing you might notice from this diagram is it's one round trip. Initiator sends a message to the responder. Responder sends a message back to the initiator. They do some computation, and then they can send data back and forth with the initiator sending the first data packet. And the one round trip part is really important. Because it keeps this idea of having static allocations and guarded state. We have authentication in the first message, so that as soon as the other side is going to operate on it and store state required for it, it knows that this indeed was an authentic packet. Okay. So just before we go into the details of it, just for those who don't know, I'll show you what the Diffie-Hellman looks like. This is a really cool property where you come up with a private key for Alice, a private key for Bob. For both of those, you can derive a public key from that private key somehow. And then we have this really awesome property where if we take the Diffie-Hellman of Alice's private key and Bob's public key, that winds up being the same thing as the Diffie-Hellman of Bob's private key and Alice's public key, with the hope that there's no other way you can compute those values other than having that information. So this is just a really cool property alone, and it's kind of amazing that we were able to find functions that exhibit this property. But anyway, this isn't new. It's just kind of great and essential for understanding WireGuard handshake. So in noise IK, which is the aspect of noise we're using, one peer is the initiator, the other is the responder. Each peer has their static long-term identity. This would be the equivalent of like what you put in your SSH authorized keys file. And then for each new handshake, we generate an ephemeral key pair. So we pick a new random number for each time we do it. And we get the security properties we want by computing the Diffie-Hellman on the combination of these. So Alice will do her static with Bob's static, then her static with Bob's ephemeral, then ephemeral with the static, and then ephemeral with the ephemeral. So all four of these. Then because of this nice symmetry of Diffie-Hellman, in reverse, the same thing will happen with Bob's static and Alice's static and so forth. And these all get computed and hashed together. And in the end, you have a shared secret that has these properties. The next two slides have more information on this that you can read in the slides on the internet, but for this talk, a little short on time, so we're going to skip over these. In the end, though, as you can see, we wind up deriving this from these four Diffie-Hellmans. We put it all into noise, and we get our session keys. So the key exchange, it might seem complicated, but in fact, it's just one round trip, and you can implement it in like 400 lines. Really a compact thing, especially compared to something crazy like OpenSSL or StrongSwan, where we have all sorts of parsers and options and things going in different directions. With WireGuard, there are no certificates, no X509 stuff. Both sides just have their short base64 public keys they exchange, and then they can talk to each other. And it's really important to keep this cryptographic core minimal so that you can really look at it and understand what it's doing. We also have kind of a poor man's post-quantum resistance, where optionally the two pairs can have a pre-shared key, which then gets mixed into the handshake. So there's this thing called Grover's algorithm, which says that if you have a symmetric encryption, the speed up on it from a quantum computer is going to be square root. So 256-bit symmetric key is going to be like a 128-bit symmetric key once we have quantum computers. And so we mix it, which 128-bit is perfectly adequate in terms of brute force complexity. And so we mix in a 256-bit symmetric key. And if that's kept secret, then even with the quantum computer, the information won't be compromised. Now, it turns out pre-shared keys are easier to steal because they're just kind of sitting around and they got to be shared at some point. But the hope is that by the time a quantum computer actually exists, all those pre-shared keys will have rusted off the hard drive anyway. And additionally, it's not a replacement for the previous handshake, it just augments it. So we still get all the same properties as before. But we can also do better than the poor man's post-quantum resistance. We can also have a kind of a hybrid post-quantum resistance, where at first we just have a normal WireGuard tunnel with no post-quantum security. And then inside the tunnel, we do one of these newfangled post-quantum key exchanges. I say newfangled because these are somewhat new. There's a NIST competition recently. There have been other things like New Hope and Enter Prime that have been around for a while, but still it hasn't seen the scrutiny that other classical algorithms have seen. And so this is not the kind of thing that we want to bake into the kernel now. But what you can do now is you make a WireGuard tunnel, and then through it, since the channel is authenticated and encrypted already, you could pick, say, 5 different of these NIST candidates for post-quantum algorithms and do them all, because you're operating over something like TCP, which is reliable, so it makes it easy to implement. And then you take the result of that and you put it into WireGuard's pre-shared key slot. So it is possible to have a hybrid post-quantum resistance. And hopefully in the future, as we get more visibility into what the post-quantum algorithms are looking like, we'll be able to build something into the core of WireGuard. But for now, I think this hybrid approach is the right way. Okay, next security design principle. We want this to be abuse resistant. Hashing and encrypting stuff is fast, but all that public key cryptography is not as fast. We're using curve 25519, which is among the fastest elliptic curve Diffie-Hellman functions, but still it's way slower than hashing and symmetric crypto. And so in something like OpenVPN, which does lots of things because it uses TLS, you can just overwhelming it, asking it to compute tons of expensive RSA or tons of expensive elliptic curve stuff over and over. So Wireguard instead uses cookies to prevent this. So a little history of cookies. We first see something cookie-like in TCP, where the initiator says, do some expensive calculations, say compute this ECDH. The responder says, okay, my magic word is area 51. Ask me again with the magic word. Initiator says, all right, I got the magic word, it's area 51. Now will you do it? And so they have this back and forth first. So this is great because it sort of proves IP ownership. And then since you know the IP, then you can rate limit based on the IP address. But then you have to keep track of this association between the magic word you just gave out and the IP address, and so you got to store state. And so this violates our dynamic allocation security design principle. Of course, also the responder always responds, and so we lose stealth with something like this. And obviously the magic word can be intercepted here. DTLS and IKE v2, that's the IPsec handshake, have something a little bit improved from this, where the initiator says compute the CCDH, the responder says your magic word is bleh, some junk, ask me again with the magic word. Initiator says, all right, my magic word is that junk, now will you do it? And then it goes. And it turns out that that junk is a MAC using some secret that the responder has that changes every few minutes as the key, and the initiator's IP address as the payload. So this is clever because you don't have to store state, since you can just recompute this MAC every time. But there's still a problem where always there is a response to the message. So it violates our stealth principle. Also, the magic word can be intercepted in the same way, and the initiator himself can be DOSed by just flooding the initiator with bogus magic words, which isn't good. As an aside, kind of out of the lineage of these ideas, there's proof of work, which is seen in the host identity protocol, where initiator says, compute this hard problem. Responder says, no way, but mine a Bitcoin first, and then ask me, and then we'll be equal. And then the initiator says, like, toil it away. I found a Bitcoin, now will you do it? And then he does it. The proof of work is great because you can make the work as hard or harder than what you're trying to prevent against being DOSed. But in WireGuard, peers can switch sides at any moment. The initiator can become the responder can become initiator. There's no client-server architecture, it's all just peers. And so we wouldn't want, say, a server that has lots of peers to be overwhelmed doing proofs of work just to talk to each of its clients. So this doesn't really fit into what we have here. But the WireGuard variant builds on the DTLS version, where each handshake message has two MACs, has MAC 1 and has MAC 2. MAC 1 is calculated as a hash that includes the responder's public key and the previous bytes of the message. And so if the MAC is invalid or missing, the message is ignored. But if it is there, then it means that the initiator knows who the responder is. It says, I'm sending this message to you, and I know it's you that's going to be reading it. And so we don't have to worry about stealth because I know it's you. So if the responder is not under load, proceeds normally, then we're done. If it is under load, then it'll respond with a cookie message. Now, the payload of the cookie itself is essentially the same as in DTLS. It's a MAC using a changing responder secret that changes every 2 minutes, the initiator's IP address. But we want to encrypt it. And we encrypt it using something public, using, in fact, a hash of the responders public key. So it's not a complete secret, but it at least assumes that you know who you're talking to. So a completely blind adversary wouldn't be able to modify it. Additionally, we use as the additional data as part of an AAD, that is some extra information that gets hashed in with the authentication tag, the bytes of the handshake message that provoked this cookie, so that when the initiator receives the cookie, he knows that it actually corresponds to the handshake message that he just sent. So then we can compute MAC2, which is just a MAC of the previous bytes of the message using this cookie as the key. And so if the MAC2 is valid, then the handshake proceeds even if we're under load. So then once we have IP address attribution, we can just do the normal token bucket rate limiting. It's an IP rate limiting algorithm. You can read any network textbook. And this maintains stealthiness since we're not responding unless we already know who it is that we're talking to. And the cookies themselves can be intercepted by someone who couldn't already initiate the same kind of exchange with the responder. The initiator himself can't be DOSed because of this additional data that we just put in, which binds the response to the handshake message that provoked it. All right, performance. We're in the kernel, which means it's really fast and low latency. So we don't need to copy packets twice between user space and kernel space. We're using Cha-Cha-20 Poly 135, which is super fast in software on pretty much all processors. Now, AES-NI is really fast too and getting faster. But actually, right now, Cha-Cha competes pretty well with it and is fast even on small MIPS boards that don't have AES-NI. The other aspect of its speed is that WireGuard's simple, and with a small program with less code, sometimes it's just faster. I mean, not always, obviously, but in this case, it's just doing less. So we have some numbers, and it beats the competition. All right, so in summary, the whole thing is less than 4,000 lines of code. It's been designed so that it can be implemented with basic data structures, nothing too funky, nothing you gotta crack open a computer science textbook for. The design of the protocol lends itself to being implemented using secure coding patterns. So, so were you to do this naively, you would probably come up with something that's at least okay. There's minimal state, no dynamic memory allocations. We want to keep it super stealthy. And it's very opinionated. So it's available for all the major Linux distros, wireguard.com/install, but it's also now we have a client for BSDs, for macOS and for Android. We're working on Windows, we're working on iOS. There's an academic paper from NDSS 2017 that kind of lays out a lot of the design rationale. It's open source, obviously. There's a mailing list. There's a free node IRC channel. And most important part is that I have this massive bag of stickers here. And if you find me after all, I'll give you a sticker. And that's it. Thanks. I'll take some questions.
Those integrations that are built in with vendors, is it just a quote-unquote supported, or what's kind of the level of integration?
So with Ubiquity in particular, it's not from the vendor. We're supplying a .deb that you can install. Okay. With the other things I mentioned, they're normal open source projects, and so they gradually trickle out to everything else.
Hi.
I'm sorry, what?
Do people have plans to push it
the FIPS 140 certification?
No, there are no plans to get this FIPS certified. I mean, we're not using AES. Probably Cha-Cha Poly should be certified at some point, but I mean, who knows? But no, we're not really seeking the FIPS stamp at all.
Yeah, just a quick question. So the Dowling-Patterson analysis that you mentioned, they weren't actually able to prove security of the WireGuard protocol as is. It required a small tweak to the protocol to prove security. Can you briefly explain what the gap was? And I'm also curious whether you think it represents a real vulnerability or if you think it's more of an academic issue.
So that's not actually the analysis I mentioned. What I was referring to is one that recently came out from Benjamin Lip in the ACCE model, which proves the properties entirely, and it's done. Now, what happened with the Dowling-Patterson paper is they wanted to prove it more traditional ECK model, where you want to have a very separate key exchange from a data plane, where you can have this key exchange in isolation and then take whatever comes out of that and put it in the data plane. This is kind of the traditional IPsec style, separate all the layers. And WireGuard was certainly not designed that way. We really intimately tie the timer state machine with the key exchange with the data plane. So we have something a lot more compact and minimal. And so if you try and analyze according to these old techniques, it doesn't work. It's not made for that. So their tweak was to add an additional message that would then put it as a separate thing. And I mean, in the end, that doesn't get us anything. And I think there's a kind of a nice hand-wavy argument you can make where you say that their analysis is, and their tweak is morally equivalent to the WireGuard protocol it is. I mean, that's the hand-wavy version. And for a while, I felt uneasy about that, but recently we have this nice computational model analysis that came out that shows we're okay.
So there's a new proof in the ACC model of the as-is WireGuard.
There is. If you go to wireguard.com/formal-verification, there's a link to it in there.
Cool. Thank you.
A question about future plans. Small and fast is good for many devices in IoT, but managing keys of thousands of devices is problematic. Do you have any plans to add a public key hierarchy of any sort? Some kind of checking a higher level signature rather than having to know every client key?
So we don't have plans to add signatures or certificates, but I think it's very feasible to build tooling around this to even manage hundreds of thousands of clients, where both sides do learn of each other's public key ahead of time. I don't think that every new protocol that uses cryptography in one way or another should reinvent the key distribution method. So by just having these short base64 public keys that are pre-distributed, you can use existing mechanisms. If you've got a database server or LDAP even, or kind of anything that's already there, you can plug into that rather than try and roll our own brand new PKI.
Hi. There's a third-party implementation of WireGuard for Windows. Have you had any communication with the developers behind that, or is your policy on that still, it's not from the WireGuard devs, so don't use it?
So we've talked a little bit with them, but we're trying to push out very high assurance software from the WireGuard project. I think our recommendation would be wait for clients that come from us because we're trying to do a really thorough job in developing it.
Thanks.
You said you were very opinionated about your crypto algorithm choice.
I'm sorry, I didn't hear.
You said you were very opinionated about your choice of crypto algorithms. Do you have a transition mechanism if tomorrow morning one of those has to change?
Yeah, so every message in WireGuard has a type. And even the WireGuard handshake itself is versioned, and that version is hashed in super early on in the handshake. And so the types of each message and the crypto that it's using are very closely bound to each other. And so if there's a cryptopocalypse and Cha-Cha is broken and everyone needs to upgrade, it's not a problem. We can introduce more message types and expand things as we need. It's very different from negotiation. It's where each side talks and what do you support and that kind of thing. It's more like what you're used to with software updates. But the protocol does allow for that kind of thing. And we even have 3 additional reserved bytes in the basic message header, just in case we need to expand massively. Oh, it looks like I'm out of time.